We present MaskSketch for unpaired structure-guided masked image generation. In this paper, we answer the question, how can we use strong prior of the state-of-the-art generative models to perform high-quality image-to-image translation without any additional supervision? Our key observation is that self-attention maps of the state-of-the-art generative transformer, MaskSketch, encode structure for images of any domains, such as photos and sketches. We use this observation to formulate a structure similarity objective that we use for a modified structure-guided sampling. Our sampling algorithm, MaskSketch, allows translation of sketches to realistic natural photos. MaskSketch translates images from arbitrary domains, such as sketches, cartoons, and 3D models, into natural domain without any pairwise supervision and only requires class label. Keep watching to take a closer look at our method. State-of-the-art generative models conditioned on text or class labels achieve remarkable realism and expressivity. However, such conditioning does not allow a fine-grained control over the spatial composition of the output image. Can we leverage the rich domain prior learned by the existing generative models to perform image-to-image translation without additional supervision? In this paper, we show that it is possible with the help of the domain invariant features. We use state-of-the-art generative transformer, MaskSketch. MaskSketch uses a VQ-GAN to encode the input image into a sequence of discrete tokens. In addition to that, MaskSketch uses a bidirectional transformer, or BERT, to sample the tokens in a non-autoregressive fashion. Starting from a fully masked sequence, we sample the tokens with BERT and mask them again with a decaying masking rate until we achieve a good generation result. MaskSketch achieves highly realistic class-conditional generation and is significantly faster than its autoregressive predecessor VQ-GAN and diffusion models such as Stable Diffusion. We have found that the self-attention maps of the intermediate layers of MaskSketch's BERT encode the information about the structure of an input image. We also see that self-attention maps are sufficiently domain invariant, since they behave similarly on the sketch examples even though MaskSketch never saw the sketch examples during training and was only trained on ImageNet. With this knowledge, we propose a modified sampling method that allows conditioning on the structure given the input image. Let us first briefly take a look at the regular MaskSketch sampling. In the regular MaskSketch sampling, at a given iteration, we start with a partially masked sequence of tokens. We pass it to BERT to fill out the masked tokens with the new token values. And we use BERT's logits to estimate the confidence scores for each of the tokens in a sequence. We then mask the sequence again to leave only the tokens with the highest confidence rate to increase sequence's realism. We repeat the procedure until we reach a certain masking rate at which we get a realistic image, usually within 15 steps. In our proposed structure-guided sampling method, we also start with a masked sequence of tokens, and we also use BERT to fill the masked token values. Instead of using the confidence scores, we use the structure similarity scores. We take the newly sampled sequence of tokens, pass it to BERT to extract its self-attention map. We compare the self-attention map with the self-attention map of the input image to compute the structure similarity scores. We then mask the sampled tokens, leaving the tokens with the highest structure similarity scores. The structure-based sampling results given a real photo indicate that if we sample using the self-attention maps of the first layers of MaskSketch, we get an almost perfect reconstruction of the input image. And if we use the self-attention coming from the last layers, the resulting images preserve the given structure and have high diversity in appearance, which is exactly what we aim for. However, when we use the structure-guided sampling on sketches, we often observe some artifacts, which is why we propose a combined sampling method that significantly improves realism and translation quality. We compute two masks, one based on structure similarity score and another one based on the confidence score that optimizes realism. We combine the two masks with a logical OR operation to sample a realistic image that follows given structure. In addition to that, we use classifier guidance to navigate the trade-off between realism and structure fidelity. Our combined sampling method allows us to do highly realistic sketch-to-photo translation on sketches of various levels of abstraction. One important thing to note here is that our method does not require any fine-tuning or retraining or any pairwise supervision. Here are a few more examples of our combined sampling results on sketches. What are the most prominent properties of MaskSketch? First of all, MaskSketch does not require any training or fine-tuning on the data from the source domain. MaskSketch is a modification of MaskSketch's inference algorithm that constrains sampling to the given structure. This way, MaskSketch achieves structure-guided generation for free. Self-attention maps used in structure-guided sampling are sufficiently domain invariant, so MaskSketch can work on images of different modalities such as sketches, cartoons, and 3D models, without any pairwise supervision and training. Compared to the supervised diffusion-based methods such as PIDI that require pairwise supervision, MaskSketch is slightly less accurate but significantly more realistic. In addition to that, it is more domain invariant since it does not require fine-tuning. One of the downsides of MaskSketch is that it involves greedy optimization in the discrete token space, which is why it does not guarantee convergence to an optimal solution. To solve this problem, we propose rejection sampling with automatic selection based on the clip features. Finally, since MaskSketch operates on the 16 by 16 token grid, it achieves limited precision, and MaskSketch sampling result may not always preserve all the fine-grained details of a given sketch. Thank you very much for your attention. Please visit masksketch.github.io for the paper and code.